All right, we want to continue to look at balancing redox reactions, but we want to add a complication that we're going to talk about as acidic conditions. Example we want to look at is balancing the equation Zn plus VO2 plus becomes Zn2 plus V2 plus. So right off the jump, this VO2 plus, we're going to start to see some kind of different cations and anions that we're not necessarily used to, but we can still understand and just apply our rules based off what information is given to us. You do not need to know the names of any of these things, but let's see how we can still balance it without knowing anything. Okay, balance the following reaction, acidic condition. So I have the Zn plus the VO2 plus, Zn2 plus, and the V. So again, we're going to start by breaking apart into the half reaction. And so we can see definitely that the zincs would pair up. You can see that the vanadium, the V here, is paired with an O. But really, we're just going to look for basically non-oxygen atoms. And we'll see why in a little bit. But basically, the oxygen is just kind of there as decoration in a way, or it's never really going to change. Oxygen is pretty strong in its oxidation state, always being -2. So as a result, we can just kind of focus in on the non-oxygen. So the Z goes to the Z, V goes to V. That looks good. So let's write those out. We're going to do each of these one at a time. I'm just going to do the whole reaction. So I have the Zn becoming Zn2 plus. Balance the atoms. Those are already balanced. It's 1 and 1. Balance the electrons. This is 0. This is +2. I'm always going to put the electrons where the positive side is, the more positive side. So that's +2 electrons. That's balanced. So that's a balanced half reaction. That is done. Then my other one is more complicated. I've got the VO2 plus becoming V2 plus. So we say that we always start by balancing atom types. Okay, so if I'm balancing atom types, I can see that my V's are okay. I have one V on the reactant side, it's in the VO2 molecule, and I have a second V on the product side just by itself. Those are not balanced at all. I got 2 oxygens on this side, 0 oxygens over here. So how I balance oxygen atoms is I add water molecules. Are these sorts of reactions, in order for it to be acidic conditions, acidic is a description of a water system. This is all aqueous chemistry. We can assume all of our electrochemistry is happening in water. So what we're going to say is basically that these 2 oxygen atoms become 2 water molecules. So we have the 2 oxygen atoms here, 2 times the 1, that's 2 oxygen atoms there, which is great. We now have accomplished having our oxygens are balanced. But our hydrogens are no longer balanced, right? We just added in more molecules, we don't have hydrogen. So how we can deal with that is we use the fact that we are under acidic conditions. What's going to happen here is that we're going to have hydrogens associated with kind of the acidic. Normally, we talked about these previously as being part of hydroniums, but we're just going to use A+. That molecule that kind of is H+, or that atom that is indicative of acidic situations of acid-base chemistry. So I had the 2 times the 2, that's 4 of these. I just add 4H+, and now I'm balanced. So whenever we're dealing with situations that are in acidic conditions, when there are oxygen atoms present, the oxygen atoms basically will transition or combine with some of these H+ to produce water molecules. So these sorts of processes, these sorts of reactions are pretty common that we could have this happen, where we could see this sort of change, where we go from the O's that were in the molecule, or in this ion, are now just in water molecules, which is you're part of solution. The water can engage in the chemistry as the solvent, and still can participate in it, and that can still happen. So this is now balanced for atoms. It's not balanced for charge. Okay, so it is more complicated to balance for atoms when you're dealing with these sorts of things, but still is a process we can follow. So this is 4 times +1, +1, +2, and that's a big 0. So again, we're looking for which side is more positive. 4 + 1 is 5 compared to 2. So we want to add negative charge onto that positive side. that would give me 3 electrons on this side. Because then that would be, I would have, that's -3, okay? So -3 plus 4 is -1, plus 1 is 0. No, -3 plus 4 is is +1, plus 1 is +2, which matches the other side. Sorry, a little too excited there. All right, so each of our reactions is balanced for atoms, it's balanced for charge. So what we need to look at now is the 2 electrons and the 3 electrons. Those need to be equal to each other. They are not here, so we have to multiply it out. Basically just swap so it's going to swap the numbers, so it's going to be 3 times my zinc goes to zinc 2 plus 2 electrons. That would give me 3 Zn becomes 3 Zn2 plus 6 electrons. And then we would want to do 2 times the 3 electrons plus the 4 plus the VO2 plus becomes V2 plus 2 H2O, which becomes 6 electrons, which is what we want to see, plus 12 H plus 2 VO2 plus becomes 2 V2 plus 4 H2O. So I've just multiplied all those out. I'm going to add these together now. In order to save space, I'm going to go ahead. These were designed to cancel out. So what I'm going to end up with is 3 zinc plus 12 H plus 2 VO2 plus becomes 3 Zn2 plus 2 V2 plus 4 H2O. A little scrunch there. Trying to save space made it worse. But that's our overall balanced equation. So let me rewrite that a little more clear. 3 Zn plus 12 H plus, kind of a big change, fine. VO2 plus becomes 3 Zn2 plus 2 V2 plus 4 H2O. And that is our overall reaction that we can see here. And so it's a balanced reaction. We can always check it. 3 zincs, 12 hydrogens. Oh, it shouldn't have been 12. That should have been 8 hydrogens. 2 times 4 is 8. I'm sorry, y'all. 8 hydrogens. 4 times 2 is 8. 2 B's, 2 B's, 4 O's, 4 O's. Good.
Participation 11.4, question 2. Balance the following reaction in acidic conditions. MnO2 solid plus Cu2 plus aqueous yields MnO4 minus aqueous plus Cu solid. This is the second question on participation 11.4 due Tuesday, November 4th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, balance the following reaction in acidic conditions. It's manganese 4 oxide and copper 2 becoming permanganate and copper.
Okay, so we've seen that when we're talking about acidic conditions, that the water starts to participate in these reactions. And generally, we're almost always doing electrochemistry in aqueous solutions, like most other chemistry that we do. And so whenever a half reaction involves oxygen as part of it, basically the water starts to get involved in the chemistry. And so when we're starting to exchange electrons between atoms that are bonded to water or oxygen, those oxygens start to interact with the water. And so you can start to think about this in some ways as like charging the water, which basically means creating ions in the water. And so there are two different types of ions that we would tend to see in water, either the hydroxides or the hydroniums. And so kind of these basic conditions. And so depending on what your conditions are, what the pH of the water is, you can control that as to what's going on in your for the solution that you're doing your electrochemistry in. So is it going to be hydroxide or hydronium? So one of the things about electrochemistry is that we do tend to use H+. Now we know H3O- is what's really there. But for the purpose of doing electrochemistry, we stick with H+. Electrochemists don't have as much respect for acid-base chemistry. And it's really kind of a focus more on the electrons. They don't care as much about everything else. The waters and the hydroniums and the hydroxides, the H+s are just kind of there to balance things out, to round it out. Plus, it will also keep things much more simple for balancing. It is definitely in your best interest, in all of our best interests, to make things easier.
Another participation question in this video. One more video left on this set. I'll see you there.